Okay, let's continue. We'll look at some examples of inequalities. So first, a basic example. Let a be greater than 0. Let a be a positive real. We can ask, are the integer powers of a so a power n is an integer. Are the integer powers of a also positive? So if we begin with a positive real a, are the integer powers also positive? So we'll look at the answer for that. It turns out yes. So note that n is greater than 0, sorry, a is greater than 0. Let n be a natural number. Multiplying the inequality with itself. So we can multiply inequalities as long as the terms involved are positive. So there's a slight modification, like, so we don't need to use that. Product of positive numbers is positive, so product, this is the basic proposition, product of positive numbers, product of positive reals is positive. Hence a power n a positive integer, is positive. Hence it suffices to show, so to show that all integer powers are positive, so we are to show, it suffices to show that so here itself I can write hence a power n is positive, or I can just write hence a power n is greater than 0. So when n is a positive integer, hence it suffices to show that a power minus 1 is positive. It suffices to show the multiplicative inverse is positive. Then we will have shown that all integer powers of a are positive. So to show is that a inverse is positive. Suppose a inverse is negative. Suppose a inverse is negative. Multiplying by a greater than 0 both sides. Since a is positive, we can multiply by a greater than 0 both sides. We have a times a inverse is less than 0. A times 0, that is 1 is less than 0, a contradiction. So if we assume a inverse is less than 0, we get a contradiction. Hence a inverse is greater than 0, and we have shown that if a is positive, then all integer powers are positive. So are the integer powers of a, namely a power n where n is an integer, also positive? It turns out yes. Right, so this is one basic example. Now another example. Consider the inequality so 2x minus 4 is greater than 5. So can we, I'll write the questions in blue. Can we simplify the inequality? So this is straightforward. So 2x minus 4 is greater than 5. This can be rewritten as 2x is greater than 5 plus 4. So to go from here to here, so this is by adding 4 both sides, you get to the, from the bottom inequality you get to the, adding minus 4 both sides, from the bottom inequality you get to the top inequality, and from the top inequality to get to the bottom inequality, if you add 4 both sides you get to the bottom inequality. Hence say both statements are equivalent. From one statement you can get to another statement, hence both are equivalent. Then so 2x is greater than 5 plus 4, so we can simplify this as 2x is greater than 9, and then you can rewrite this as x is greater than 9 by 2. Why? Because from here to here, from bottom to top, multiply by 2. So I'll just write mult, or I'll just write the full thing, no problem. So from here to here, multiplying 2 from lower inequality to the bottom inequality to the top inequality, multiplying by 2 will get you there, and from top to inequality to the lower inequality, multiplying half will get you to the, from the top to get to the, from the top inequality to get to the bottom inequality we can multiply both sides by half. From the bottom inequality to get to the top inequality we can multiply both sides by 2. Hence this equivalence holds. So I'll write this equivalence is because of this, and this equivalence is because of this. Hence we have simplified. Hence we found an equivalent inequality of 2x minus 4 greater than 5, namely, so the inequality 2x minus 4 greater than 5, saying 2x minus 4 is greater than 5 is the same as saying x is greater than 9 by 2. So we have found an equivalent inequality. So we have in a sense simplified the inequality. So here's a somewhat better example. So consider the inequality so this is the inequality 3x plus 5 by x minus 4 is less than 2. We can ask the same question, can we simplify the inequality? So we'll proceed. So first note that, so we have the denominator x minus 4, so we can consider this combined constraint. Instead of considering the constraint 3x plus 5 by x minus 4 is less than 2, we can consider the stronger statement 3x plus 5 by x minus 4 is less than 2 and x is less than 4. Suppose we are looking at this statement, then we can rewrite this as, so 3x, so then x minus 4 will be negative, so 3x plus 5 will be greater than 2 times x minus 4 and x is less than 4, right? So if x is less than 4, this denominator will be negative, and so from getting from here to here you are multiplying by x minus 4, and from getting from bottom to top you are multiplying by 1 by x minus 4. So both the statements are equivalent. Saying 3x plus 5 by x minus 4 is less than 2 and x is less than 4 is same as saying 3x plus 5 is greater than 2 times x minus 4 and x is less than 4. So in this situation, in this statement x minus 4 is negative. So yeah, we can rewrite this condition as this, and we can further rewrite this as, so this is x is greater than minus 13 and x is less than 4. So if and only if, so minus 13 is less than x, which is less than 4. So we have rewritten one statement. This is not needed, this is understood. So we have rewritten, instead of rewriting the constant 3x plus 5 by x minus 4 is less than 2, we have rewritten the constant 3x plus 5 by x minus 4 is less than 2 and x is less than 4. This stronger constant can be rewritten as minus 13 less than x less than 4. Now note that, now let's consider the another version. Note that another condition, 3x plus 5 by x minus 4 is less than 2, this will remain the same, and we instead demand that x is greater than 4. Let's say we demand that. Note that this statement, both of these holding, this can be rewritten as 3x plus 5 is less than 2 times x minus 4 and x is greater than 4. So this can be rewritten as x is less than minus 13 and x is greater than 4. So minus 13 is somewhere here, so x is here, x lies here, x lies here. So this is impossible, right? So this is impossible. X cannot lie in both instead of, so the diagram is a little bit confusing. X can't be both greater than 4 and, or can be true, but and cannot be true. It cannot be both greater than 4 and less than minus 13. So this is impossible. So we have found that 3x plus 5 by x minus 4 less than 2 and x greater than 4 is impossible. Hence, so the original constraint, the original inequality, so 3x plus 5 by x minus 4 is less than 2, this can be rewritten as 3x plus 5 by x minus 4 is less than 2 and x is less than 4, right? We begin with less than 4. Or 3x plus 5 by x minus 4 is less than 2 and x is equal to 4. Or, so 3x plus 5 by x minus 4 is less than 2 and x is greater than 4. So exactly one of these three cases will hold, but this is impossible. I'll write it below this probably. So this is impossible and even this is impossible. We saw that, so x equals 4 is impossible because the denominator in the first constraint has x minus 4 terms. So this is impossible, and x greater than 4 we saw it is impossible. Hence, so in this OR statement, so we get that this is equivalent to 3x plus 5 by x minus 4 is less than 2 and x is less than 4. Only this is possible. So we have rewritten the original inequality as this, and then this we saw that it reduces to minus 13 is less than x less than 4. Hence, the original inequality 3x plus 5 by x minus 4, saying 3x plus 5 by x minus 4 is less than 2 is the same as saying x is strictly between minus 13 and 4. So this is a somewhat better example to illustrate the power of casework. we found that the other two cases are impossible, hence we got this simple expression. A simple rewriting of the statement 3x plus 5 by x minus 4 is less than 2. It can simply be rewritten as, the constant can be rewritten as minus 13 less than x less than 4. So yeah, this involves casework, and these are more or less the basic examples. So that's all for this part. See you in the next part.